Welcome, children. I'm Sanjana Agarwal from Chanakya Tutorial, and we are here to facilitate physics and understand the physics at its best. It seems to be difficult, but actually it is not. So, first of all, children, we are going to take up chapter light, reflection, and refraction. Okay, here we begin. Before proceeding to understand the applications of light, mirror, lenses, etc. in our daily life, let us understand what is light basically. Although we have been learning about light in earlier grades also, but light is a form of energy which helps us to see the surrounding, which makes us see, which makes the things visible in our surrounding. Apart from this, light is a form of electromagnetic wave. It is a type of electromagnetic radiation. It travels in a straight line. This property of light is known as rectilinear propagation of light. Also, it does not require any medium to travel. It travels at the highest speed in vacuum, which is approximately 3 into 10 raised to the power 8 meter per second. Light is made up of tiny packets of energy called photons, as well as it also exhibits the wave nature. So these are few characteristics about the light. Moving ahead, the very first comes the law of reflection of light. I hope everybody knowing this, what are the laws of reflection? It says that angle of incidence is equal to the angle of reflection, and this law is followed everywhere, irrespective of the type of surfaces. Next, the incident ray, the normal to the mirror at the point of incidence, and the reflected ray, they all lie in the same plane. But most important is the first one. Remember, children, that angle of incidence is always equal to angle of reflection. It will be followed everywhere. Now, making of a plane mirror. Plane mirror we all use every day, which has a flat plane surface. One of its surface is reflecting, another surface is opaque surface. When we look into the mirror, we find the image obtained of ourselves in the mirror, which is, you can say, a virtual and erect image. It has many other characteristics, and we'll be learning about it soon. Okay, types of reflection. Yeah. So if reflection of light makes ourselves visible in the mirror, why not all other objects also give us the clear image of ours? There is a difference. The type of surface on which the reflection is taking place makes the difference in regular and irregular reflection. So reflection through the smooth surface, that is a plain glass, still water. Okay, whenever the surface is absolutely plain with no disturbance or bumps and depressions in the surface, if we allow a parallel beam of light to be incident upon the surface, because at every point the normal will be same, because the normal, that is perpendicular line on each point of incidence is same. So suppose we try to make the light incident at 30 degree, the reflected rays will also be making 30 degrees. You can see, children, that here all the reflected rays are also parallel. That's why we get a clear image of ourselves in the plane surfaces, which is known as regular reflection. Whereas, suppose you take a fabric or you take a wooden almirah, the surface, if you touch, comparative to the plain glass, do you find any interruptions in the surface? Do you find the surface irregular? Yes. It does not seems to be by just looking at it, but while touching, we can feel that yes, the surface is bit irregular. If I make a zoom in view of that surface, let us say that it has some bumps, it has some depression. Now, again, if we try to make the ray of light, beam of light incident at 30-degree angle, the point where the ray is falling do not have the same normal. Like if this surface, the normal is like this. At third point, the normal is like this. When the normal, the perpendicular lines at each point of incidence are not parallel, the reflected rays will also not go parallel. So you can see that the reflected rays are moving in random or different directions, which do not gives us the image at all, and it just makes us see the makes the thing visible to us, and no image is obtained. Because of the reflected rays not being parallel, we do not get any image. Such kind of reflection is known as irregular reflection. So reflection through concrete wall, running water, or any other thing like the door, or you can say the fabric, the material which you are using right now to study. I'm using the material for writing, etc. Each of these object is reflecting back the different or irregular reflection. Now, when we see the image of ourselves in a plane mirror, what are the characteristics? You must have noticed. If we are standing in front of mirror, do we find ourselves upside down? Have you ever noticed your head down and legs up in the mirror? No. So same side is up. Our head is up and our toes are down. So that this type of image is known as erect image. That is whenever same side in the image is up and same side is down, it is the erect image. The image is also of same size. Do you find yourself taller than your actual height or shorter than your actual height? No. So these are two characteristics. Mirror image is erect as well as same size. Also, image is at the same distance behind the mirror as the object is in front of it. If you are standing, suppose at 2 meters from the mirror, you will find your image also standing at 2 meters. If we take a step ahead towards the mirror, our image also takes the step ahead. Just one difference. The image in a mirror is laterally inverted. Laterally inverted means whenever we raise our right hand, our image raises its left hand. Whenever we raises our left hand, the image raises our right hand. So no vertical inversion, just lateral inversion. Please note the characteristics of image, children. Okay. Let us understand this more clearly with the help of an example. Suppose a robot is standing at a distance 8 meters away from a plane mirror. You can say this is the object, as left side is acting as the reflecting surface of the mirror and the right side is the painted side, or you can say opaque side. At what distance from him will his image be formed if he is standing at 8 meters? Very clearly, as per the characteristics, the image will also be obtained at 8 meters from the mirror. So if question asks you that at what distance is the image of the robot from the robot? So it will be 8 plus 8, 16 meters. Now, if he moves at distance of 2 meters towards the mirror, if he moves 2 meters towards the mirror, that is this time the object distance is 6 meters, the image will also move 2 steps ahead the mirror, and the distance of image from the mirror will also be 6 meters. So overall, the distance between the object and the image is gonna 6 plus 6, that is 12 meters. Very simple. After the plane mirror, children, we have spherical mirrors. Now comes the real part of this chapter, spherical mirror. So spherical mirror, first of all, just imagine a ball. All the spherical mirrors that we use as spectacles, they are carved out from the spherical part only. Do you have to imagine this? Okay. So whenever, like, look at this red surface, it has the outer surface reflecting. The arrow points the outer surface of the sphere is reflecting. Such kind of surface is known as convex surface. And whenever we have the inner surface of a sphere as reflecting, that type of surface is concave. I'll give you one more example. When you can take the example of a spoon. When you take the front surface of spoon, which we use to eat, okay, that front surface is curved inwards. So that inward curved surface is concave surface. Whereas if you take the back surface of spoon, the back surface is curved outwards. That type of surface is also always known as convex surface. So this example is a bit simple to understand. Okay. The front surface which is used to eat is concave surface, and the back surface which is curved outward is the convex surface. Moving ahead. Yeah. So we have two types of mirror based upon the identification or recognition of mirror on the basis of the inward and outward surfaces. The convex surface is also known as diverging mirror, and concave surface is also known as converging mirror. Okay, why diverging mirror first of all? Whenever we allow the parallel rays of light to be incident upon the diverging mirror, that is convex mirror, okay, they reflect back in such a way that if we produce them back, they appear to be coming from a single focus point. Okay, so because actually on the reflecting side, if we look at the mirror, the rays are getting diverged. You can see they are moving apart because the actual rays are diverging and the image is obtained inside the mirror or behind the mirror. That's why this mirror is also known as diverging mirror. And in contrast to the diverging mirror, we have converging mirror, which has the inner curved surface as reflecting. So if we allow a parallel beam of light to be incident upon the concave mirror, the rays will be reflected back on the same side of mirror. Okay, because of this, all the points, all the rays get focused at a single point, which is also known as the principal focus. We'll be learning the ray diagrams as well, don't worry. So that's why, because all the rays actually converge at a single point on the same side. They are converging, they are meeting at a single point. That's why this mirror is known as converging mirror. I hope it is clear to all. Now here comes few common terms that we use in case of spherical mirror. The first one is the center of curvature. Children, like every circle or every sphere has a center. These mirrors also have a center point because they are a part of a sphere only. Okay, like we have a ball and we have carved out this much surface. This is acting as a converging mirror, sorry, diverging mirror. And if we have carved out this piece, actually they are a part of different spheres shown in the single diagram. Okay, this is acting as a concave mirror. So every sphere, the mirrors also has a center point, which is known as a center of curvature. So center of curvature of a mirror is a center of sphere of which mirror is a part. The geometric pole, okay. I'll show you this with the help of a diagram. I'll be drawing a concave mirror here. So center of curvature, let us assume that this is the center of curvature of this spherical mirror. Now what is pole? The geometric center of the spherical surface of the mirror is called the pole of mirror. Children, before moving to the pole, this reflecting spherical surface which we have for reflection, this is known as the aperture of mirror, and the midpoint of this, the center point of this mirror is known as the pole of mirror, represented by letter P. Now, principal axis is a straight line joining the pole of mirror to its center of curvature. If we join the center of curvature to the pole of mirror, we get this line. We can extend this line ahead, which is known as the principal axis, and denoting here with P dot A, but this is principal axis. Next come radius of curvature. The distance of center of curvature from pole. Every distance in the mirrors is measured from the pole. So this distance is known as the radius of curvature. Children, all the parameters, all the terms will also be used in case of convex mirror as well. Moving ahead. We have few more common terms, that is real focus and virtual focus and focal length. Okay. First of all, let me draw the same diagram for convex mirror as well. Now, here comes the difference, because in convex mirror, we have the place, the side where we'll be having the center. This side is opaque. Let us say this is a pole of convex mirror. If we join this, we get principal axis. So if we allow a parallel beam of light here in case of concave mirror, they will converge at a single point, and that point will be on the same side of reflecting surface. Okay, so this point will be known as the principal focus because of all the parallel rays getting converged, getting focused at a single point. That's why this is known as principal focus. But what in case of convex mirror? If we allow parallel rays of light or the rays of sunlight, you can assume, because it is at infinite distance, the rays of light will be diverged. They'll be reflected back in such a manner that if we produce those rays back, they will appear to us like they are coming from a single point, which is known as principal focus. So this point here will be acting as principal focus. If you look at the reflecting surface only, the rays are moving apart. They are not going to meet on the same side. Okay. Now read here. Concave mirror, the reflected rays meet at a point F on on the principal axis. This point is called focus of concave mirror. Why it is known as the real focus, children? Because light rays are actually meeting here. I missed to draw the arrow. These light rays are actually meeting on the same side of reflecting surface. That's why. Now, why the focus point of convex mirror is virtual? A convex mirror, the reflected rays do not meet at any point, but appear to come from a point F on the principal axis behind the mirror. This point is called focus of mirror because they appear to come. They are actually not meeting at this point because that side is opaque. So they appear to be focused. That's why the focus of convex mirror is known as virtual focus. Next, the focal length, like radius of curvature, the distance of the focus from the pole of mirror is called the focal length of mirror. From the pole, if you measure the distance of focus, this is represented by small f, focal length. And if you measure the distance of focus, in case of convex mirror, again, this is represented by small f, focal length. But as per the sign convention, focal length of concave mirror will be negative always, and focal length of convex mirror will be positive always as we have to move towards the right side. So you remember the Cartesian plane, children? Never get confused. It's very simple. You all know about Cartesian plane. Right side means positive x, left side means negative x, topmost positive y, and the bottom side is negative y. So consider this origin of Cartesian plane as the pole of your mirror. Now moving to right, left, up, down. Accordingly, you have to take the sign of the respective parameters. Let us move ahead. Yeah, one more thing, that the principal focus, the focal length of mirrors is always equal exactly the half of the radius of curvature. That is, in case of any mirror, if suppose the pole and the center of curvature, that is the radius, suppose is 10 centimeter, then focus will always be exactly at the half distance, and in present case it will be 5 centimeter. It was just an example. Now here comes the question. Find the focal length of a convex mirror whose radius of curvature is 32 centimeter. Children, we need to find the focal length. We just have seen that focal length is half of radius of curvature. So radius of curvature is given 32 centimeter. As per Cartesian plane, in case of convex mirror, pole is here, Center of curvature is here. So radius will be measured towards the right, that is positive 32 centimeter. 32 divided by 2, we get 16 centimeter focal length. Next, the focal length of spherical mirror is 20 centimeter. What is the radius of curvature? Keep practicing, children. Focal length of spherical mirror is, this time focal length is given 20 centimeter. What is its radius of curvature? Okay. So focal length is only 20. That is no negative sign, which is positive. That means it is asking for convex mirror again. So radius of curvature equals twice of focal length. You know that focal length is always half of radius of curvature. So you can say that radius is twice of focal length. Putting up the value, we get R as 40 centimeter. It's very simple. Okay. So now we are moving ahead to study the ray diagrams. What are ray diagrams? Ray diagrams just help us to locate the image, the nature of image, the size of image, whether it is smaller in size, whether it is large, etc. Because plain mirror only gives us the same size image, but spherical mirror not always give the same size image. It varies. So just by looking at the mirror, because you often find these kind of mirror at different places, at public places, like this is the back surface of spoon. If you look at this, it will give you the erect and the magnified image. Next, this object, size of object. Here you can see in the third diagram, inverted image, the girl must be holding the spoon. Yeah, her head is up and toes are down, inverted, vertically inverted image. Next is a diminished. Why diminished? Because in just a small mirror, you can see how wider the view it is giving to us. Means the size of image is smaller, but the view is wider. So this type of image is diminished image. Children, there are certain rules to easily draw the ray diagram and locate the image. See, why do we study the rules? Because suppose if I give you a single point and I ask you to draw a line, children can draw this multiple, infinite number of lines can be drawn. But if I give you 2 points, everybody must be drawing this line only, isn't it? So at least two intersection of two rays is required to locate the image. That this point of intersection will give us the image. Out of 3 or 4 rules, you can use any 2 rules. It's your choice, not mandatory. Okay. The first rule says a ray of light which is parallel to the principal axis of a concave mirror passes through its focus after reflection. If you allow the parallel incident ray to principal axis that falls upon the mirror, after reflection from the mirror, it will pass through the focus only. Next rule is a ray of light which passes through the center of curvature of a mirror will be reflected back along the same path. Now, why it is so? Because in a circle or in a sphere, if we join the line from center to circumference at any point on the circumference of the mirror or the sphere, that is the normal itself. Means it will be, if I take a tangent here and draw a perpendicular line, so this is making 0-degree incident angle. As per the law of reflection, the angle of reflection will also be 0-degree, and that's why any ray that is passing through the center of curvature will be reflected back along the same. Rule third says, if a ray of light passing through the focus of a concave mirror becomes parallel to principal axis after reflection. This is exactly opposite to the first case. In that case, a ray parallel to principal axis passes through focus after reflection. Here, if the ray is passing through the focus, then after reflection, it will get back uh, parallel to principal axis. And the fourth rule says, a ray of light which is incident at the pole of concave mirror is reflected back, making the same angle with the principal axis. This is a bit similar to the second rule that, not same, I'm telling similar. So this principal axis is also passing through the center of curvature. And if it is already meeting the circumference of this or the point on this mirror only, this principal axis is actually the normal on this at this particular point. So if suppose the ray makes 45-degree angle incidence angle with the normal, the angle of reflection will also be 45 degree. So if it strikes at the pole of mirror, it will get back making the same angle from the mirror. Okay, this is just a summary of the 4 rules that we have just discussed. Now, these are very important. We have a few ray diagrams. Like in concave mirror, we have 6 cases in all. Because in case of concave mirror, the reflecting all the parameters, the center of curvature, focus, etc., they all lie on the side of reflecting surface only. So we can have multiple cases, like beginning from the object we are keeping at infinite distance. We'll try bringing our object closer to the mirror, and we'll see how the size and nature of image varies. So very first case, if we if we have the object at infinity, for infinity we can consider, let us allow the rays of light to fall upon the concave mirror. What will happen? As discussed, why it is known as converging mirror. This is the answer. If in case question ask you to explain along with the diagram, this has to be drawn in that particular question. Okay. So parallel rays of light are allowed to pass to fall upon the mirror. You can say sunlight. After reflection, they will pass through the focus. Another ray below the principal axis, if it strikes the mirror again after reflection, it will pass through the focus. Because they both are meeting at a single point focus, children, the nature of image will be real, because the image which is obtained on the same side of reflecting surface, it is not visible in the mirror. You have to place a screen in order to see the image. Okay, the image will be inverted and it will be highly diminished. Like if you allow the rays of sunlight and you just hold a piece of paper here, you will see a very small and a bright spot at the focus point only. You have to try this, moving paper close and away from the mirror. Definitely you will get it. Let us move to the next diagram and bring our object closer to the mirror. Now object will be kept in the range, not at infinite distance. So let us keep the object beyond C. Okay, that is beyond center of curvature. We have allowed a straight parallel ray of light to be incident upon the mirror. After reflection, it will pass through the focus point. As you can see, children, it is not mandatory to take the rays. The rule which we have taken, you can take any two, you will get the same spot and same nature of image. No variation will be there. Second case, if a ray of light is passing through the focus, and after being incident and reflection from the mirror, it will go parallel to principal axis. So you can say the rays are meeting at this point between C and F. So image will be obtained between C and F. Children, did you note one thing? When our object was at infinite distance, the image was highly diminished. It was almost point sized. What how much size you can expect of a sun if it is obtained on a piece of paper, while the size of sun you can imagine. Okay, so the size had bit increased. Nature of image, you can see it is upside down, inverted. It is on the same side of mirror, real, and diminished. Not highly, but still it is diminished because it is smaller than the size of object. Let us bring our object more closer and keep our object at center of curvature. Center of curvature, okay? Again, the two same rules. Children, actually these two rules, no, when we allow a ray of light parallel to principal axis and after reflection passes through focus, another passing through focus parallel to principal axis, they are bit simple to be taken, okay? So draw this diagram by your own, practice on your own. You'll get the intersection point exactly at the center of curvature, below center of curvature. So in this particular case, we get the same sized object, same sized image. It will be inverted, it will be real. You must be noting one thing, children, that real image is always inverted. Yes, real image will always be inverted. And this particular case, only single case in concave mirror, like a plane mirror, we always get same size. In concave mirror, if we keep our object at center of curvature of the mirror, we'll get the same sized image. Bringing our object more closer and keeping it between F and C, focus and center of curvature. This time, again, taking the same rules, same rays of light, parallel to principal axis. After reflection, it passes through focus. Then if it is passing through focus, it is going back parallel to principal axis. Now, bit changed this time. When our object was at infinity, image obtained was point size. When our object was within the range and beyond C, the size bit increased. When our object was at C, it was of same size. So did you know that gradually the size of image is getting bigger and bigger? This time, if our object is between C and F, the size of image is increased compared to the size of object. Okay, so just keep these few basic points in your mind. You know, it will help you to solve the numericals very quickly. So this time, the nature of image is again real and inverted, but magnified because it is greater, larger than the size of object. Okay, if we keep our object at F, focus point only, the straight parallel to principal axis, a ray after passing through, after reflection is passing through focus, and a ray passing through center of curvature. This time we have taken a ray of light which passes through center of curvature will be reflected back along the same path. So children, these are getting converged, but they seem almost parallel. They seem parallel, but it means they will converge at a very large distance, a very large distance. So that means the image must be getting bigger. The image will be highly magnified this time, but real and inverted. So as we are bringing our object closer and closer, the size of our image is getting bigger and bigger. Okay. Next case is a special case of concave mirror. Now let us keep our object between F and P, between pole and focus. Children, see, look carefully. First of all, the sky blue ray, a ray of light parallel to principal axis. After reflection, it passes through the focus, and another ray from center of curvature will be reflected back. Okay. I also want to draw this diagram once. Please look at it because this particular case is used in many of the applications. Children, was just one thing I would like to tell you, that suppose in your notebooks, in your answer sheets, because you will be using ruler, if you take 4 centimeter, uh, the distance of 4 centimeter through by the help of your ruler for considering center of curvature, then mark focus exactly at 2 centimeter. If these measurements are correct, you are not going to get the incorrect answer or incorrect spot for the image formation. So we have kept our object between F and P. Let us allow a ray of light. A straight ray, which is parallel to principal axis, will be reflected back along the focus, and a ray of light that is passing through the center of curvature, it will be reflected back. Now, this time on the same side of mirror, in all other cases, the image was converging either at in the range or with out the range. Okay, but here they are getting diverged. They are not going to meet at least on the left side. So what we have to do, produce these ray of light on the back side. Why I'm drawing dotted? Because this is the opaque or painted side. The rays are actually not here. It will just appear to us. Means this image, for this image, we do not have to place any screen because the image is not obtained on the left side. It is behind the mirror. Because they are intersecting at this particular point, can you see the image obtained this time is erect for this particular case. The image is magnified as well. It is erect and it is virtual because no screen is required here. I hope you have got it. Now, this particular case is used by the dentist. Why they use concave mirror? So, because they hold the mirror very close to the teeth and they can get a magnified view of our teeth. Okay. We'll tell you more of concave mirror. So just have a quick look at this particular page and you can have a glance over the ray diagrams, that where we keep the object, where the image is obtained, what was the size of image and what is the nature of image, just for a quick revision. We also have to practice numericals because they are the important part of this chapter. Let us solve your numericals. A concave mirror has a focal length of 10 centimeter. Focal length, concave mirror. Okay. Concave mirror has negative focal length. So it will be -10. Where should an object be placed in front of this concave mirror? Means U is to be find out so as to obtain an image which is real, inverted, and same size as that of object. Very simple. While discussing, I highlighted that case a lot, that when you get the same size image in case of concave mirror, yes, whenever we keep our object at center of curvature, we get it. That is the point, you can say the U should be equal to twice of F. That is at the radius of curvature only. I'm writing, or you can take radius of curvature, that is twice of 10 is 20 centimeter. It is only magnitude given here, but if you write -20, that's also fine because concave mirror has negative focal length, it has negative radius of curvature as the distances are measured to the left side. Got it, children? Next question. We wish to obtain an erect image. We wish to obtain an erect image of an object. Erect image using a concave mirror. Oh, again, children, if so, that is clear now. If you have practiced ray diagrams properly twice or thrice, you will not fail in solving any numerical. Concave mirror, when it gives erect image, only in one single case, whenever our object is in between pole and focus. Okay. Focal length is given 15 centimeter. What should be the range of distance of the object from the mirror? It's very simple. If we keep our object from pole to focus, that is from pole up to 15 centimeter towards the left, that is in the front of mirror. So the object should be placed at any distance which is less than 15 centimeter from the mirror, will be getting erect image. What is the nature of image? The nature of image will be erect, and erect image is always virtual. Also, it will be magnified. Is the image larger or smaller than object? Of course, it will be larger. Draw a ray diagram to show the image formation in this case. So we have just drawn this diagram in the ray diagrams. Please practice. Okay. Read out the question, children. Sunita takes a mirror which is depressed at the center. Can you tell me what type of mirror is it? Depressed at the center, and mounts it on a mirror stand and erect an enlarged image of her face is formed. Okay. She places the mirror on a stand along a meter scale at 15 centimeter mark. Okay. So on the meter scale, she has not taken 0, but 15 centimeter mark. In front of this mirror, she mounts a white screen and moves it back and forth along the meter scale till a sharp, well-defined inverted image of a distant tree is formed. Okay. Distant tree is formed on the screen at 35 centimeter mark. Fine. Name the mirror and find its focal length. As yeah, as the real and inverted image is obtained, inverted image is only given by concave mirror. Okay, because convex mirror always give the virtual and erect images, and so the mirror is concave only. Find its focal length. What will be the focal length, children? Very simple. Because on the mark, suppose this is our scale, she has placed the mirror at 15 centimeter already, the mirror, and the screen was placed at 35 centimeter, where exact image of the tree was obtained. So because we know that in case the object being at infinite distance, all the rays of light focuses at a single point. So this is going to be the focus. If she would have kept the mirror at 0 mark, then 35 would be the answer only. But here she kept the mirror at a 15 centimeter on the 20 centimeter. This 35 is only the point of focus from the mirror. But just because mirror is not placed at 0 mark, that's why we have to subtract 15 from 35. Got it? Next, why does Sunita get sharp image of distant building of 35 centimeter mark? Because incident rays are parallel to each other. After reflection from concave mirror, they meet at focus. This is a property of concave mirror. And they produce a sharpest image at focus only. So this you have to check, by moving your screen. And you will get at a particular point. Yeah. From the given table, showing object distance and focal length of 3 concave mirrors, answer the following question. Object distance is in centimeter, focal length in centimeter, object distance 30, focal length is 20, object distance is 10, focal length is 15. When focal is 15, then object is kept at 20. Out of 3, in which case the mirror will form the image having the same size as that of object. So in order to obtain the image of same size, we need to keep our object exactly at twice the focal length or at center of curvature. If focal length of a mirror is 10 centimeter, twice of focal length is 20. And if the object is kept at 20, we'll definitely be getting same size object image. Draw the ray diagram. So just take the focal length as 15 centimeter, not 15 on your answer sheets. Children, you can take 2 to 3 centimeter as focal length, whatever the range is yours, and keep object distance accordingly. Or if you can take your sheet, in the landscape mode and draw a neat and clean diagram if these terms are in your range. So please practice the diagram. Okay, so here come the uses of concave mirror. Concave mirrors are commonly used in torches, searchlights, and vehicle headlights to get powerful parallel beam of light, because we know whenever we keep our object at focus, the image is obtained at infinite distance. That means all the rays of light after striking from the mirror, they are pass straight to the longer distance and meet at a very high distance, at infinite distance. So this property is being used in the searchlight, vehicle headlights, etc. They are used as shaving mirror, because in the last case, when our object is between the pole and focus, we get a larger image, magnified image in the mirror only. We do not need any screen. Dentists use concave mirror to see the larger images of teeth, same property. The last case, of ray diagram. Large concave mirror are used to concentrate sunlight to produce heat in solar furnaces. This makes the use of first case when we allow a parallel beam of light to be incident on the concave mirror. They get focused at a single point. So this concave mirror will allow the heat and light of sun to be focused at the single point, and it will help our food to get cooked. Concave mirrors are also used in doctor's head mirror, same property, to concentrate the light, on beam on the small area of the body, parts such as nose, throat, etc. Now comes the convex mirror, children. So again, the rule for making ray diagram is same. If your parallel beam fall on a convex mirror, the rays of light will appear to diverge from the mirror, and they will appear like they are coming from the focus point only. Ray of light after striking the mirror will be reflected back. If I take another ray from the below the principal axis, it will also be reflected back in such a way that if we produce it back, it will appear to us, to be coming from the focus point only. But on the opaque side behind the mirror, always draw the dotted lines. Do not draw the solid line, because this is actually not the reflecting surface. Another rule, ray directed in the direction of center of curvature of a convex mirror is reflected along the back along the same path. If a ray of light is directed along the center of curvature, I told you, children, center of curvature to any point on the circumference is like a normal 90-degree line. So that means the incident ray is making 0 degrees. Next rule is the opposite of the first rule, which says that if ray of light is directed towards the principal focus, after reflection, it will become parallel to principal axis. You can see the ray of light, the incident ray of light is directed towards the focus, but after reflection, it is going back to principal axis. Okay. And the last case, again, if a ray strikes the pole of the mirror, so this principal axis is acting as a normal or perpendicular. So whatever angle it makes with the pole, that is principal axis, is the incident angle. The same angle would be for the reflection, and hence the light will be reflected in such a manner. Again, using any of these cases, you can draw the ray diagrams for convex mirror as well. So this is the first activity. You can see the sky blue rays. Okay. Whenever they fall parallel to principal axis, these will be reflected in such a manner that if we produce them back, they will appear to us to be coming from the focus point. And this is why this mirror is known as the diverging mirror. And this focus is known as a principal focus, because rays appear to be coming from the single focus point. And actually on the reflecting side, the rays diverge, they move apart from each other. So nature of image is virtual, it is erect. You can see, because it is formed, behind the screen. We do not need any behind the mirror, and we do not need any screen, but the image will be highly diminished. This convex mirror forms diminished or smaller size images. Because on the reflecting side of mirror, we do not have any parameter, focus or concave mirror. So wherever we keep our object within just the range, but not at infinity, the image obtained will have the same nature for any placement of, for any distance of object. If we allow a straight beam of light parallel to principal axis, after reflection, it will appear in such a manner that it is coming from the focus point. And another case, if the ray of light is directed towards center of curvature, it will be different for you. That's a pole, principal focus, center of curvature. We have kept our object here. A parallel ray of light, parallel to principal axis, will be reflected such that if we produce it back, it will appear to be coming from focus. And if it is directed towards center of curvature, it will be directed, it will reflect back on the same path. So the meeting point is here, you can say, uh, near to the focus only, means between the pole and focus behind the mirror. So the image obtained in case of convex mirror. So this is a very common example of shop security mirrors of convex mirror, that at public places you'll always find such mirror which gives us the smaller size images, but we do not have to do anything with the larger images. We just need a wider field of view. Okay. Children, why is convex mirror only used as a rear view mirror in vehicles also? Why cannot we use a plane mirror or concave mirror? So convex mirror, by its nature, the rays of light which are coming from, a wider view, they converge at a point. Like you can say, it gives a wider field of view with a smaller sized images, which is the greatest property to be used in the public places. And what happens with the plane mirror? That it gives us a narrow field of view. So on the other hand, plane mirror gives a narrow field of view. That's why we cannot use. And why concave mirror? In most of cases, they give us inverted images. Okay, so that's why they cannot be used. Name a mirror that can give an erect and enlarged image of object. Erect and enlarge. It is a concave mirror because in case of convex, we get erect, but those are not enlarged. Those are diminished. Remember this. Children, let us summarize. And what is the difference between a concave and convex mirror? So concave mirror has a silvering. Concave mirror has the silvered part or the painted part on the outward curve side, whereas convex mirror has the outward side reflecting. Okay, bulging surface is reflecting in concave mirror, and the inward curved surface is reflecting in concave mirror. It converges the light rays incident on it after reflection, and convex mirror actually diverges the light rays. The concave mirror image formed by concave mirror is real as well as virtual. In last case, it is virtual also. But in convex mirror, in all the cases, image obtained is virtual for all position. How can you identify the type of mirror? By just looking at it, and if you are not allowed to touch it. So if the image is upright, it is of same size and it does not change in size. So that type of mirror is a plane mirror. Otherwise, if you get, um, the erect and enlarged image, the mirror is concave. But if you get the in smaller sized image, then the mirror is convex, like this. Now the Cartesian sign convention, children. It's very simple, as I've already gave you an idea. Like keep Cartesian plane in your mind. Whenever you move towards right, it is positive. Object will always be kept towards the negative side only. So you will always be negative. Okay. Now image sum will always be obtained sometimes on the positive side. For moving towards positive y, it will be if the image is erect, then the size or height of image will be taken positive. And if it is inverted, we have to move down, then the height of image will be negative. Simple. Every distance is measured from the pole. Like in Cartesian plane, we measure the distance from optical center. Here we have to measure distance from the pole. Children, this is a mirror formula which says 1 by V, V is the image distance, U is object distance, equals to 1 by F, that is the focal length of mirror. To find the magnification, means the size of image has reduced or it has increased, it will be given to us with this formula, H2 by H1, or sometimes you will find in a few books H dash by H, HI by HO, depends, any by any alphabet you can represent. Or it is always equal to minus V by U. Okay. Children, please note that this is straight line only. This is a negative sign only, single negative sign with V. Okay. Let us solve few questions. An object is placed An object is placed at a distance of 36 centimeter from a concave mirror. So U is given minus 36 centimeter because object is always placed to the left side. Focal length 12. Okay. Focal length of a concave mirror is also always negative. So minus 12. Find the image distance. Very simple, children. Use this formula. 1 by F equal 1 by V minus 1 by U. Substitute the values. 1 by minus 12 equals 1 by V we need to find out, and minus of minus 1 by 36. Simplify, keep 1 by V here. It will be minus 1 by 12, minus 1 by 36. And after solving, you will get the value of V as 18 centimeter. The more you will practice the numerical, student, you will develop more and more confidence. So 18 centimeter, at this distance, the image will be obtained. Next, at what distance from a concave mirror? Okay, let us practice one question from the convex mirror. This you can pause and please solve on your own. An object placed 20 centimeter in front of a convex mirror. Object is placed 20 centimeter, so U is minus 20 as object is always to the left side. Found to have an image 15 centimeter behind the mirror. Remember, children, the image in convex mirror is always to the right of mirror, so it will be positive 15 centimeter. Find the focal length. Again, simply just apply the formula. 1 by 15 minus of minus 1 by 20. Oh, sorry, I just made a mistake. This is positive. So solve this, simplify the expression, and you will be getting focal length as 60 centimeter. Okay. So here is another numerical based on convex mirror only. Children, you can pause the video and solve on your own. Let us practice more numericals, not just based on the mirror formula, but based on formula magnification is given by height of image to height of object, or it is given by negative of image distance to object distance. Okay, children, many cases, you'll get this question as MCQs, that if magnification of an object is a +1, -1, -0.5, etc. What does it mean? So magnification has two parts. One is sign, another is numeric value. Sign tells you like you are moving upside or downside of the pole. So if it is positive, that means you are moving upper side, and it means the image is virtual. If you are moving bottom side, that means the image is inverted. And we already know that virtual image is always erect and inverted image is always real. If now the numeric value is equal to 1, the numeric value can be equal to 1, h dash by h. If h dash equals to h, then only magnification will be 1. That means the image and object are of same size. Now, if you are getting the value greater than 1, that means height of image would be greater, It means height of image is greater than h, means if numerator of any fraction is greater than denominator, then only we can get the value greater than 1. And if it is opposite, that is h dash by h is less than 1, when it is possible, if h is greater than h. So greater than 1 means image is magnified, and lesser than 1 means image is diminished. Few questions to practice, children. The magnification produced by a plane mirror is +1. What does this mean? Erect plus means the image obtained is erect, and 1 means same size. So erect image is always virtual and it is same size. What is the nature of image formed by concave mirror if magnification is +3? Positive means again it is erect. Erect is always virtual, and 3 greater than 1, that is magnified. What is the nature of image formed by a concave mirror if magnification is minus 0.75? Minus means you are moving to the bottom side of the principal axis. That is inverted image, which is always real. And 0.75, the numeric value is less than 1. That means the size of image is smaller than the size of object. Another question, let us practice. Complexity level has increased here in this question. An object 4 centimeter in height. An object 4 centimeter in height. Let us take h, it is 4. Place the distance of 36 centimeter from a concave mirror. Okay, u is minus 36. Image is formed 18 centimeter in front of mirror. Front of mirror means on the same side. So we will always be also be taken negative of 18 centimeter. Height of image. Children, we are not asked to find focal length. Neither we have to. Neither we are given. So no need to use the mirror formula. Dash by h equals minus v by u. Put the value. Height of image is to be found out. Height of object is 4 equal minus minus 18 to u is minus 36. So here we are getting h dash as negative of 4 by 2, that is minus 2 centimeter. The height of our image is minus 2 centimeter. Minus means it is inverted. Inverted image is always real, and 2 means it is magnified. So just by looking at the, okay, sorry, it is not magnification. So just ignore this part. Otherwise, negative sign shows that image is real and inverted. Now, children, again, there are many more questions to practice. So pause the video and start solving. Another question based on the magnification formula, plus you have to use mirror formula also here. Same, similar type of question based on magnification. There are ample of questions, children. You can keep practicing. Okay, here comes another, the next part of this chapter, which is refraction of light. So what do you mean by refraction of light? It means when the light has to change its medium, it undergoes propagation. It changes its path many a times. So change in the direction. of propagation of a ray of light when it travels obliquely from one medium to another. Transparent medium should be transparent only. Light cannot pass through opaque medium. This phenomena is known as refraction of light. So here, okay, we'll move to the glass slab later. Let us understand the basic phenomena further. What happens when a ray of light moves from rare to denser medium? If air is the first medium here, water is the second medium. So air is acting as a rarer and water is acting as a denser medium. It will always bend towards the normal. Keep this in mind. Rare to denser, the bend in the light will be towards the normal. That is, velocity decreases if the refractive index or the medium goes denser. Next, if it has to pass from denser to rarer. Suppose the water is the first medium now, air is the second medium, it will bend away from the normal this time. That is, if the medium is getting rarer, the velocity of the ray of light will increase. Denser to rare, away from the normal. But in the case, it has to be incident normally on any surface. In that case, it will pass straight. It will pass undeviated and the velocity again decreases because the medium is changing or the medium is getting denser. Okay. Now, practice a few questions, children. They will help you enhance your understanding. If a ray of light strikes the glass slab at 30 degree, okay, this is the normal. If a ray of light strikes a glass slab at 30 degree, what is the angle of incidence? The angle 30 degree is given with the glass. So that means remaining angle 90 minus 30 is 60 degree. What is the angle of incidence? Tell quickly. This will be 60 degree. Moving to next. If a ray of light strikes the glass slab normally, what is the angle of incidence? This case we just have seen. You just have to tell the angle of incidence. If a ray of light is striking, parallelly along the normal only. If this is a normal and ray of light, incident light is also along the normal, very simple. The angle of incidence is 0 degree. Okay, it is 0 degree. If a ray of light strikes the glass slab at 30 degree, now what is the angle of emergence? Think about the answer quickly. Okay, the previous case only. Still, I'll draw again. So if a ray of light makes 30 degree angle with the glass slab. Children, first thing, this is not incident angle. Incident angle is always measured with the normal. This is our incident angle with the normal. Now, a ray of light will undergo bending towards normal as the medium is getting denser. Again, this at second interface, light has to move from denser to rarer. So it will go away from the normal. Okay. But children, note one thing, that angle of incidence in case of glass slab will be equal to angle of emergence because the medium are same for and the two surfaces, the two interface where light has to undergo refraction are also parallel. So the light rays are parallel. If you just produce the incident ray further, you'll see that these are parallel as well as angle of emergence will be same. So yes, angle of emergence will also be 60 degree. I hope you're getting it. A ray of light strikes a glass slab at angle of 50 degree with the normal to the surface of slab. Now you tell this. 50 degree with the normal to the surface of slab. What will be the angle of incidence? Yes, it will be 50 degree only. A ray of light gets deviated when it passes obliquely from one medium to another medium because it is because of color of light changes, frequency changes, speed of light changes, or intensity changes. You are correct, because the speed of light changes. Next, Rakesh performs the experiment of tracing the path of ray of light passing through a rectangular glass slab for different angles of incidence. He observes that in all cases, I will be greater than R, but I equals to E. Okay, let us read the question again. Rakesh performs experiment and light is passing through a rectangular glass slab. So light has to change medium from air to glass, rare to denser. At the first interface, light will undergo refraction and will bend towards normal. That is, angle of refraction will get smaller than the incident angle. So incident angle will be greater, but I will be equal to E, because the two mediums where incident and emergent ray are there, they are same. So I will be, what do you think? Yes, I will be greater than R, but I will be equal to angle of emergence. Let us learn the refraction of light, like reflection. There are few phenomena. Yeah. Laws of refraction says the incident ray, the refracted ray, and the normal to the interface of two transparent media. And important ratio of sine of angle of incidence. The ratio of sine of angle of incidence to sine of angle of refraction is a constant, and that constant is known as refractive index. But this is for the light of a given color and for the given pair of media, means this is comparative. Okay, depending upon which is rarer, which is denser. This law is also known as Snell's law of refraction. Okay, here is an application to the refractive index. When we keep a pencil in a glass or a jar filled with water, it appears to be bent. Why is it so? Because of refraction. Let me give you one more example, children. If you just put a lemon in a glass or a transparent tub filled with water, let us say this is filled with water. You have played lemon here. Okay. Now the observer is standing here and is looking from the top. So ray of light which is coming from the lemon. This is a ray of light. Now at the point of incidence, we have to draw normal. Because the medium is changing from denser to rarer, the ray of light will pass away from the normal, that is that way. Okay. Another ray, let us assume the next ray here. Drawing normal again, and it will also pass away from the normal. So if we reduce these rays back, because they are getting diverged, in case of diverged images, we have to produce the images back. So can you see this blue line? They are meeting at this particular point. The image of lemon or the lemon will be appear to the observer quite raised above. The image, the position of lemon will be this for the observer, but its actual position is this. So this all happens due to refraction. Okay, so children, this part is sometime get confusing, but no worries, because here I'll help you to understand it very clearly. See children, whenever you put suppose this is medium 1, this is medium 2, the light is undergoing refraction from here. So whenever you write sine I by sine R, okay, this will give you the refractive index of medium 2 with respect to 1. So every time you use the formula sine of angle of incidence to sine of angle of refraction, you will not be getting refractive index of that first medium with respect to second. No, you will be getting refractive index of second medium with respect to first. Okay, there is one more formula. If we are knowing the speed of light in the two mediums, let's say this is V1, this is V2. Then speed of light in medium 1 to speed of light in medium 2 will also give us the value of refractive index of second medium, the medium in which the light is entering with respect to the first medium. Okay. Now, if you change these medium, suppose the ray of light is moving from, you take the second medium, same here. The first medium is here now. Next, the light, because the light has to undergo, denser to rarer, it will move away from the normal. Okay. And this time, if I take sine I by sine R, the I and R will change. Or you can say refractive index of medium 1 with respect to 2 will be given to us. Or in simple terms, if you want to understand, you can just say that everything will get reciprocal. That is, if you want to take refractive index of medium 1 with respect to 2, you have to invert the direction. So velocity 2 with respect to velocity 1 will give you the value. Now children, see, if you multiply these two expressions, if you take V1 by V2 into V2 by V1, what you will be getting? V1 by V2 was eta 2, 1 multiplied eta 1, 2. So these terms are velocities, the speeds are going to cancel, and you will be getting eta 1, 2 into eta 2, 1 equals to 1. Or you can say that eta 2, 1 equals to 1 by eta 1, 2. That is refractive index of medium 2 with respect to 1 will be the reciprocal of refractive index of medium 1 with respect to 2. Got it? The refractive index of diamond is 2.42. What is the meaning of this statement? Very simple. Refractive index of diamond is 2.42 suggests that speed of light in diamond will be reduced by a factor of 2.42 to its speed in air. Let us understand this with the help of formula. So refractive index of diamond with respect to air only. Okay, because it is absolute refractive index. So speed of light in air to speed of light in diamond. Now it is given 2.42. Speed of light, we know generally it is denoted by letter C also. To speed of light in diamond, that is C by 2.42. It means whatever the speed of light in air is, it will be reduced by 2.42 factor compared to the speed in air. So it means this. Next comes the few formulas for refractive index. So whenever we take refractive index of, okay, let us assume that speed of light in vacuum to speed of light in any other media, it will give us the refractive index of second medium with respect to first medium. Similarly, if speed velocity of light in air is given and then the light is entering in ice, so you will be getting refractive index of ice with respect to air. Okay, again, this is the refractive index of glass with respect to vacuum. Vacuum or air means the same in these particular cases of refractive index. Either you write vacuum, either you write air, doesn't differ. This is a refractive index of water with respect to air. Again, absolute refractive index of water. Whenever you compare the refractive index of anything with air, or the light is entering in any medium through air, that means you are getting the absolute refractive index of the second medium of the other medium other than the air. Similarly, Ri of oil with respect to air. Okay, these formulas we just have seen. So have a glance. You can pause the video and note these important points to help you solve the numericals in exam. If the first medium is not mentioned, take first medium as air, it is understood. If first medium is vacuum, Then refractive index of second medium is called absolute. And for solving numericals, always take the value of speed of light in vacuum as 3 into 10 to the power 8. One more important thing, refractive index is in both the formulas. It is the ratio of two similar terms. So the unit gets cancelled. That's why refractive index has no units. It is unitless. Let us solve few numericals. Light enters into a glass plate having absolute refractive index 1.5. What is the speed of light in glass? Okay. Light is entering into a glass plate having absolute refractive index 1.5. What is the speed of light in glass? Fine, not difficult. And G with respect to vacuum. If you write vacuum, that's okay. If you do not write, it's understood, but okay, let us write it. So that means if the absolute value is given, that means light is entering the glass medium through vacuum. So velocity of vacuum will be numerator and velocity of light in glass will be denominator. Put the values. It is V is 3 into 10 to the power 8 and Vg we need to find out, simplify, solve and get the answer. It is 2 into 10 to the power 8 meter per second. Very simple. Okay, children. Next is refractive index of water is 4/3 and speed of light in air is given. Find the speed of light in water. Again, you can use the same formula and you'll get the answer. If the refractive index of water for light going from air to water is this much, again, absolute refractive index of water is given to you, then what will be the refractive index for light going from water to air? Okay, very simple. Seems bit difficult, bit tricky, but it is not. Yeah. So refractive index of water going from air is 1.33. This is a refractive index of water with respect to air, or you can say the absolute one. Then what will be the refractive index for light going from water to air? That means water to air means you have to tell this is water with respect to air. Now we have to tell air with respect to water. We know the two opposite medias, the ray of light going from one to another, and then opposite is a vice versa. So just by using this formula, calculate and you will get the answer, which is 0.75. Again, please take a pause and solve this question. Refractive index of kerosene, turpentine, and water are given. In which of these material does light travel fastest? Keeping in mind the formula that refractive index is speed of light in air to speed of light in medium. From this, speed of light in medium will be equal to speed of light in air to refractive index. Very obvious from the relation. If it is asking in which of these material does the light travel fastest. For this to be fastest, the refractive index should be least because they are inversely proportional to each other. So refractive index is least for water. That means speed of light will be highest in the water medium. Another good question. The path of light passing from air to different media A, B, and C for a given angle of incidence is shown below. Study the diagram and answer the following question. Okay. In which of media A, B, and C has maximum optical density? Maximum optical density. Okay. So if you remember, because angles are given here, we have to use this formula this time, not the velocity one. Sin I by sin R equals to refractive index of second medium to the first medium. Okay, there are three different A, B, and C. Which of the media A has maximum optical density? So for maximum optical density means maximum refractive index. For eta refractive index to be maximum, the value of refraction should be least. In which of these cases angle of refraction is least? For A, 30 degree. Sine 30 is least, then sine 40, then sine 45. So that means refractive index of A is greater as per this relation, then refractive index of C, and then refractive index of D. Through which of three media will the speed of light be maximum? Speed of light is maximum in medium B of lowest refractive index. Okay. Let me write for this also, on which how we can relate this with the speed of light. Speed of light in air to speed of light in given medium. So speed of light in the media is again inversely proportional to, sorry, this is Vm. Speed of light in any medium is inversely proportional to its refractive index. So if speed maximum will be is asked here, that means refractive index should be least. Refractive index of B is least. That's why the speed of light will be maximum in B. Will the light traveling from A to B bend towards or away from the normal? A to B. See the relation between A and B. A is denser than B. So if light passes from A to B, that is denser to rarer, that means it will bend away from the normal. So here we have come to the lens part, children. Lenses are again, they have many uses in our daily life. You must have seen that they are used in magnifying glass, spectacles, contact lenses, telescope, microscope, and binoculars. Let us study that how they obtain the images and how they are used in these variety of instruments. Okay. Again, like mirrors, we have lenses, converging and diverging lens. So very simply, if we keep two convex surfaces together made up of glass, this is a solid complete material, it gives us the converging mirror. Two convex surfaces forms joins to form a converging mirror. And if we combine two concave surfaces, this is the diverging mirror. Or converging mirror is convex in nature because two convex surfaces have joined here, and diverging mirror is concave in nature. So just simply telling you to, make everything easy. Convex lens has the similar nature like concave mirror, and concave lens has similar nature like convex mirror. Rethink. Okay, now if we allow a parallel rays of light to be incident upon the converging or convex mirror, because it is similar to concave mirror, it will converge the rays. It converges the rays, and the rays actually meet at a single point. That is again at the focus only. So this focus is known as the principal focus and is the real focus for convex mirror. Similarly, if we allow parallel rays of light to be incident upon concave mirror, like the convex mirror, they will diverge, and because they are not going to meet on the right hand side, we have to produce it back. So they will appear to be, coming up from a single point, which is known as the focus. And because the rays are actually not meeting on this other side, they appear to meet. So that is why this focus is a virtual focus. Okay. Now, difference to be understood between concave and convex mirror. Lens which has two spherical surfaces curved outwards is called convex lens, like two convex mirrors or two convex surfaces have been placed together. And when two concave surfaces are placed together, it forms a concave lens, which are curved inward. So convex surface has a, the middle part thicker and thin at the edges, narrow at the edges, whereas the concave mirror is thicker at the edges and thinner at the center. Convex lens is converging in nature because it actually converges the rays. Diverging lens is Concave lens is diverging in nature because it diverges the rays, and the images are then produced, images are obtained by producing back the images, rays back on the opposite side. It forms a real focus, actually meeting the rays. It forms a virtual focus, which appear to be coming from the focus. It is thick in the center and thinner at the edges. This I have already told. Now, again, the common terms will be used in lenses also. So very easy to understand if you have understood the concept of mirrors. So when rays of light parallel to principal axis are incident on a convex lens to a point on the principal axis of this point is called the principal focus. And F1 and F2 actually they have, if we just look at the two surfaces, we'll get two foci. But this one is known as the real focus, where the image actually converges. And again, like in mirrors, we used to measure and take all the distances from pole. Here we'll be taking all the distances from optical center. This will be acting as our origin compared to the Cartesian plane. So like shown in the picture, focal length of convex mirror will always be positive and image obtains on the left side actually. So focal length of concave mirror will always be negative. Okay. Distance between the optical center and principal focus is known as the focal length. The rays, the rules are same, means similar. Now just have a look how the rays will pass. Incident ray, if it is parallel to principal axis, because refraction is taking place, it will not go back reflecting in the same medium, but it will pass on the other side, passing through the focus. Fine. Next rule says, if the incident ray passes through the focus, then it will go straight parallel to principal axis. And the third rule says, if it passes through the optical center, again, dear children, this if any ray passes through optical center, it means it is like, incident at any surface normally. So you remember that if any ray of light is incident perpendicularly to any surface, that will pass undeviated, similar to this case. You can use any of these rules to obtain the image formation. Now here comes the object ray diagrams for convex lens. Convex lens is similar to concave mirror because we have, we'll be placing the object at different distances here. So let us first take the case when the object is at infinity. This has been already discussed. When we keep our object at infinity, the rays of light will converge at a single point and will the image will be obtained point sized. Again, if you allow the sunlight to be incident upon convex lens, they will converge at a single point and the image will be real and inverted, obtained at the focus. Next come, if we bring our object closer to the lens, that is not at infinity, but in the range only. So it is kept beyond 2f1. If the object is kept beyond 2f1, take first ray as, passing straight parallel to principal axis. It will pass through focus and another ray through optical center. These two rules actually, they seems very easy. If you also follow these now, it will be easier for you. Another ray passes through optical center, will pass straight. So you can see that the image is getting obtained between f2 and 2f2. The size of image is smaller than the size of object. So again, because it is obtained on the other side, you need a screen to be placed. Object form will be real, it will be inverted and smaller in size. Next is object at 2f1. It is like placing the object at center of curvature in concave mirror that used to give us the same size image, okay, and real inverted. So see, almost similar. First rule, straight ray parallel to principal axis will pass through focus, and another ray passing through optical center will pass straight, being in incident perpendicularly. So they are meeting at 2f2. That is like another center of curvature. Image obtained will be real inverted and same size. Again, children, you can draw these ray diagrams by your own. You will definitely find it very easy. Let us bring our object more closer between f1 and 2f1. Okay, straight parallel ray passing straight parallel to principal axis and will pass through focus after refraction. Another ray through optical center will pass straight. Now, did you note that again the size of image is getting increased step by step? So in previous case, when we kept our object at 2f1, image obtained was of same size at 2f2. Now, and in previous case than the earlier one, they were smaller in size in the object. This time, after same size image, we have got a larger image. So the image will be enlarged. Image obtained will be real inverted and 2f2. Children, one thing I would like to tell you again, if on your notebooks or your answer sheets, with a ruler, if you are taking 2 centimeter for f1, then please mark 4 centimeter for 2f2, so as to get the correct and exact location of image. And similarly on the right hand side also. Object at f1. If we keep our object at f1 and allow a straight ray of light parallel to principal axis, it will pass through focus, and another ray will pass through optical center. Okay, it will pass straight. So they almost seems parallel. So they'll be meeting it after a long distance. So we can say that at infinity, the object image will be obtained. But yes, it will be real and inverted and it will be very large. This is a similar case to the concave mirror. We used to keep our object between pole and focus, principal focus. Here we have kept our object between focus and optical center. So what's going to happen? The rays on the right side are getting diverged. Here they are getting diverged. We have to produce back the rays. So, see, here in the last case, we'll be getting virtual and erect image. And yes, it will be enlarged. You can compare all the 6 cases of convex lens and concave mirror. You'll find these same, means similar. Let's answer a few questions. Where should an object be placed in front of a convex lens to get a real image of the size of object? Size of object, children, same size of object. Very simple. Which parameter is similar to center of curvature? Twice the focal length. Okay. Now, if one half of the convex lens is covered with a black paper, will this lens produce a complete image of object? Justify your answer. It's a very interesting question. Suppose, children, if lower half is covered with a black paper, it is all black. Now, if any object is placed here, this is our object. Do you think that we'll be getting the image on the other side, the complete image? Yes, because the rays of light are still passing. The 2 rays of light are required for the intersection of image, and we'll be getting the image properly. But what will be the difference? Because the other part means the half of the beam has been blocked by the black paper. So the image will not be that much bright. Okay, lens will produce a complete image of object, but intensity of image is reduced because rays from the top portion is only refracted and rays from the bottom surface have been blocked. So just intensity will differ, otherwise image obtained will be complete. Now children, you can again quickly have a glance over all the cases of convex lens, where the object is placed, what is the location of image, the size of image, and the nature of image. What are uses of convex lens, children? So convex lenses are used in making microscopes, using their all the cases properties, telescopes, light projectors, so as to focus an image on the screen, making a simple camera, magnifying lens by watchmaker, and is also used in spectacles to correct defect of vision called hypermetropia. You must all have learned about this. We will also be taking up human eye and the colorful world chapter after this. Now, the rules for concave lens. If you have already, mastered the ray diagrams, drawing ray diagrams of both mirrors and convex lens, then this is nothing. Okay. So first rule says, again, because this is a diverging mirror, the rays of light will be diverged. Okay. If you allow a parallel ray of light parallel to principal axis, it will diverge and refract in such a way that will appear to be coming from the focus point. Okay, so if you are drawing it, children, just telling you trick how to draw it correctly. Just place your ruler at this point and this point, means such that these 2 points are joined, and then you can draw a ray and produce it back. It will be very easy. Next rule is a ray of light passing through the optical center. Again, because this case, acts, any ray passing from the optical center will be acting as a normal perpendicular line. So that's why the ray passes straight undeviated, without any deviation, without any bend. Third rule says a ray of light going towards the focus of concave lens becomes parallel to principal axis after refraction. So you can just place your ruler, at any point passing that is oriented towards F2, directed towards F2, and then you can draw it straight parallel to principal axis. Now, because this is a diverging lens, it is similar to the diverging mirror, that is convex mirror. So not much cases, only 2 simple cases will be here. If we keep our object at infinite distance, of course, any rays of light from infinite distance will be parallel only, no doubt in this. And parallel rays of light will be diverged. If you remember, this is the first rule we have just seen. Okay, it will diverge in such a way that will appear to be coming from the focus. Secondly, if we take another ray below the principal axis, it will again be refracted in such a way that if we produce it back, will be appear to us coming from the focus point. And the image obtained will be virtual, erect, because it is not on the other side. It is like we have to produce it back to get the image. That's why the image is virtual. Virtual image is always erect and it will be smaller in size. If we bring our object in the range, not infinity, but somewhat will knowing its distance of object, then first rule, ray of image, passes straight parallel to principal axis. Incident upon the lens will refract such a way that is coming appear to us coming from the focus, and another from the optical center will go straight. So you can see the intersection point of the 2 rays. Okay, the image is again virtual because we have to produce back the ray. Virtual is always erect and it's clearly smaller than the object. Why, sorry, where the concave lenses are used, because they only give us the virtual erect and smaller images. So these were used in Galilean telescope, in high quality lens system for optical instrument, because this is very common, spy hole in doors, because they also give smaller size images and a wider view, and also using spectacle to correct a defect of vision called myopia, where people can see the near objects clearly but fail to see the far objects. Such an interesting question. What type of lens must be placed? What type of lens must be placed at XY So that image I shifts to I dash. Imagine that the lens XY is not present here. In that case, okay, let me take another pen. If we take this ray of light, if you just imagine that none of the lens is present at this place, then this is our ray of light. Okay, we have to shift it to I dash. What we have to do? We have to decrease the converging power of lens. And so we'll be using concave lens because it has negative focal length. It has negative power. Moving to the next question. This you try on your own. The image of a candle flame formed by a lens is obtained on a screen placed on other side of lens. If the image of is 3 times the size of flame and the distance between lens and image is 80 centimeter, at what distance should the candle be placed from the lens? Okay. So the case given is image of candle flame formed by a lens is obtained on a screen placed on other side. Which type of lens obtains the real image? Only convex and on the right hand side. So image is 3 times the size of the flame, that is magnification is -3. Why minus? Because real image is always inverted. Distance between lens and the image, that is image distance is 80, so it will be positive 80 centimeter. Where should, at what distance should the candle be placed? We need to find out. Okay. Simply, we can use the formula of magnification, which is V by U for lens. It is minus V by U for mirrors, but it is V by U for lens. So substitute the value -3 equal 80 by U. We'll be getting U as 80 by minus 80 by 3. Please divide, you will be getting U as 26.67 centimeter. So object to be placed, the image is real and the lens is a convex lens. Children, again, the sign convention will be same for the lens case also. Anything towards right will be positive, towards left will be negative, top positive and bottom negative. And every distance to be measured from the optical center. Now, the lens formula is just slight change from the mirror formula. Mirror formula is 1 by V plus 1 by U equals 1 by F. Lens formula is 1 by V minus 1 by U equal 1 by F. Again, magnification is H dash by H in case of mirror also. But in mirror, in terms of image and object distance was minus V by U. But here we have V by U. Same phenomena and same notations. If you have object and image size equal, magnification will be 1. That means object and image are of same size. If numerator is greater, the image height of image is greater. If the height of image is greater than height of object, then overall magnification will be greater than 1. And if height of image is less than the height of object, that is magnification will be less than 1. And the third case is, okay. Now let us solve few questions based on lens formula. Yeah. If an object of height 7 centimeter is placed at a distance of 12 centimeter from the convex lens, U is to the left always, so negative, of focal length 8. Focal length of convex lens is always positive, so positive 12. Find the position of image. Okay, so we can use lens formula here. 1 by V minus 1 by U equals 1 by F. We need to find out V only. We can already amend the formula. That is 1 by 12 minus 1. Sorry, I made some mistake. Focal length is 8. Yeah. Focal length is 8 minus 1 by 12. Children, you can simplify the expression and you will get the answer as 24 centimeter. So position of images 24 centimeter. Fine. Similar question. Convex lens of focal length. This time you are given with the focal length 10 centimeter. Distance of 12, u is given, focal length is given, u is given. How far from the lens should an object be placed so as to form its real image on the wall? Object distance we need to find out. So please again use the same formula and try to get the answer quickly. And it will, the more practice you'll do for the numerical part, no, you'll develop the speed that is highly required if you have numericals. And it will also help you in, solving questions in mathematics. So please keep practicing numericals. A boy was standing. Okay, next let us solve one question from the concave lens. A boy was standing at distance of 20 centimeter from a convex lens. Oh, this is of convex lens again. Just a moment, children. Children, third and fourth question, you can take a pause and solve. I want one question of convex concave lens to be explained here. Yeah. So an object is placed at a distance of 50 centimeter from a concave lens. Again, the object distance will be negative as always. A focal length 20. Focal length of concave lens is again always negative, so minus 20 centimeter. Find the nature and position of image. Okay. Using the lens formula, 1 by v minus 1 by u equals 1 by f. Nature of image, that is 1 by v, we have to get. Along with me, children, please keep practicing. Minus 1 by 20, minus 1 by 50. Take the LCM, solve the expression. You will get minus 14.28 centimeter. So as image distance is negative, image is obtained, and we know that concave lens always give us the virtual and erect images. So image will be virtual, erect, and on the same side of concave lens. Here is another question based on this is based on convex lens actually, because object distance is this and image obtained is on the right side. Okay. You can pause the video and start solving the question. Here is another question. An object is placed at distance of 15 centimeter from a convex lens. If the focal length of lens is 60, find the image distance. Similar question, same formula to be used. Children, you have ample of questions to practice. Let's come to the other type in magnification part. An object 6 centimeter tall is placed in front of a convex lens. Object is 6 centimeter tall, okay? Placed in front of convex lens at a distance of 18 centimeter. U is also given 18, so minus 18. Image is formed at a distance of 9 centimeter. V is also given. If the lens is convex, image is obtained at 9 centimeter on other side, that is positive 9. Then find the height of the image. So I don't think we need to use lens formula here because we have h, v and u. We have h also. We just need h dash, that is the height of image. So it is equal to magnification equals h dash by h equals v by u. Substituting the values, we'll get v by u into h. This is 9 by minus 18 into 6. Children, you can solve. So we'll be getting minus 3 centimeter as the height of image. It's very simple. You just need to practice. Okay, moving ahead. The next question is again similar. An object 10 centimeter tall is placed in front of convex lens at distance of 30 centimeter. If image is formed at a distance of 5, height of image. No need to take up the lens formula, but only this magnification part will work for you. Another question, another set of question which involves the lens formula as well as magnification one. Keep practicing, children, for your exams. Okay. An object 5 centimeter high is held 25 centimeter away from a converging lens of focal length 10 centimeter. Find the position, size, and nature of image formed. Also draw the ray diagram. Okay, let us solve this question. Which one is the converging lens, children? Convex lens. So object is 5 centimeter high. Okay, 5 centimeter high. So height is given to us. Away from a converging lens of focal length 20. Convex lens focal length is always positive. So positive 10 centimeter. Find position, size, and nature of image using the H is given to us. 25 centimeter away, U is minus 25. We can use lens formula very first of all. 1 by F equal 1 by V minus 1 by U. We can get 1 by V out of here. 1 by F plus 1 by U. Simplify the expression, children. You'll be getting V as 1650 by 3. I'm writing V as 50 by 3. Nature, okay, size of image also is to be find out. So we can use the formula H dash by H equals V by U, as we have H here by 5 equals V is 50 by 3 and U is minus 25. So that will be equal to minus 2 by 3. That is H dash will be equal to minus 10 by 3. That is equal to minus 3.33 centimeter. Okay, so as the height is negative, that means the image is inverted. Inverted is always real, and the image height is 3.33. The object height is 5. So fine. There is another question for you to practice. Now comes power of a lens. So what do you mean by power of a lens? Power of a lens is actually the measure of the degree of convergence, that to what extent the lens is gonna converge or diverge the rays, so as to obtain the clear image on the retina or wherever it is we are gonna use it. Okay, so power of lens is defined as the, in terms of formula, we can say it is a reciprocal of its focal length. Power equal 1 by F, or we can say that focal length equals 1 by power. In case okay, here the formula is written. P equals 1 by F, where focal length should be in meter only. If focal length is in meter, then the SI unit of power is diopter. Please, if in case in question, the focal length is centimeter and all the calculation is going in centimeter and power is asked to you, convert the focal length in meter, then only tell the answer in diopter. So often it is asked, what do you mean by 1 diopter? You can write 1 diopter means if the power of a lens, if the focal length of a lens is 1 meter, its power will be 1 diopter. Simple. Here is another concept about power of lens, combination of lenses. So, you know, if number of lenses are placed in close contact, then the power of the combination of lenses is equal to the algebraic sum of power of individual lenses. Like, just remember this formula. Power of number of lenses which are combined together will be the algebraic sum of the power of the individual lenses. Okay, don't do this with the focal length, because power is the algebraic sum of the combination of individuals, not the focal length. Just for example, if two lenses of power P1 and P2 are placed in contact with each other, then the resultant power is given by, let us say, convex lens power plus 4 diopter is combined with concave lens of minus 10 diopter. Apply this formula, P equals P1 plus P2. Do not forget the sign. Power and focal length are reciprocal, but they'll always have the same sign. Okay, so if focal length of convex lens is positive, the power of convex lens will be also be positive. If focal length of concave lens is negative, the power of focal length will also be negative. So considering the sign, put this value 4 minus 10 minus 6 diopter, that is overall the lens will be concave in nature. Moving ahead. Few questions based on power formula. A convex lens of focal length 10 centimeter. What is its power? It's very simple. Focal length is 10 centimeter positive, that means convex lens. So first we need to convert it in meters. For converting into meter, 1 centimeter will be 1 by 100, that is 0.1 meter. Now apply the formula for power, that is 1 by F, 1 by 0.1, that is 10 diopter. Okay, power is positive, that's why the lens is convex. Calculate the power of a convex lens of focal length 20 centimeter. Again, just in place of 10, you have to make it 20, you will get it 5 diopter. The next question, children, you are supposed to solve it. Find the power of concave lens of focal length 2 meter, very straight. Simply 1 by F, 1 by 2, that is minus 0.5 diopter, and the lens will be concave. Thin lens of focal length minus 25 centimeter. What is the power of lens and what is its nature? Focal length is in centimeter again this time. So minus 25 centimeter. That means minus 25 divided by 100. We get minus 1 by 4. If it's your choice, if you feel comfortable in dealing with the fractions, then do not convert decimal. Power equals 1 by F. So minus 1 by 4. Okay, we have got power as minus 4 diopter. A person having a myopic eye uses a concave lens of focal length 50 centimeter. What is the power of lens? Children, please keep solving. There are ample of questions here. You can pause the video and solve. The power of a lens is 2.5 diopter. What kind of lens it is and what is its focal length? All the questions are based on just single formula, P equals 1 by F, or it can be written as F equal 1 by P. Okay, let us solve one question based on power of lens. Two thin lenses of power plus 3.5 diopter, and P2 is minus 2.5 diopter placed in contact. Find the power and focal length of the lens combination. So combination, the lens after combination will be P equals P1 plus P2 plus 3.5 minus 2.5, that is 1 diopter power. And now we need to tell the focal length of this combination only. F equals 1 by P, it will also be positive 1 meter. Okay, children? Fine. So this was all about light chapter. I hope if your doubts were there, they must have been clear. And if you are still left with any doubt, children, I'm here for you. You can comment. Please like and subscribe to the channel of Chanakya Tutorial. We will definitely get back to you to solve your queries, and keep practicing, because practice will only help you develop confidence, and also it will help you to speed up in solving the questions. Thank you, children. Bye-bye.